This is a problem from Chapter 4, OpenStack's textbook. What's it called? College Physics. Let's get to it. I've already drawn a picture. And the question has two superheroes hanging from rope. I guess they're on the same rope. Yeah. And so the superhero, let's just call this Superhero A and Superhero B, just because I don't want to write Trusty and Sidekick or whatever, it doesn't really matter. Mass of 95 kilograms, mass of 55 kilograms. And so we want to A, draw free body diagrams for Superhero A, Superhero B, and the rope. It says the rope. I'm going to draw two. I guess I'm going to draw two ropes. I haven't decided yet. Let's just go with it. Because the rope's kind of tough. Because it's not clear. And then we want to find the tension above Superhero A and in between these two. Two tensions, at least three force diagrams. Let's start with Superhero B, because that's the easiest. So let's draw a force diagram. Here's B. I'm just going to draw a dot. When we draw a force diagram, we don't need to draw the whole object. Later we will, but for now, no. Now, we need to think, what long-range forces are acting on B? What is acting on B that doesn't have to touch? And the answer is gravitational force. So I have a downward gravitational force. I'm going to go ahead and write that as mg, and I'm going to draw it as a vector going down. And I'm going to call this mbg. And g is a vector, don't forget. So g is the vector negative 9.8 newtons per kilogram y hat. Okay, so I'm using y hat for my notation for my y component. I've said before, some places use I, some places use I, J, K, X hat, Y hat, Z hat, and there's other notations. This is what I'm going to try to stick to because this is the way the book writes it. Okay, so if you're using I hat, J hat, and K hat, I don't know if maybe you're not using the book, or you've seen it before. I don't know. Okay, but that's just, I'm letting you know where I'm at. So we have the mass times the vector, downward force. Now, other than that, the question is, what's touching Superhero B? Because we are the other kind of forces we would have are contact forces. The only thing touching that we could really consider would be the tension, the string pulling up. Okay. Now, you could say, oh, the air is pushing on the person too, and that is technically true, but that's a very small force. We can ignore that. So the other force would be, I'm going to call this T1. And that's going to be the tension in the string right there. That's it, right? That's it. Now, if I want to draw a nice diagram, I would have the length of this and the length of that be the same, because the length of the force arrow is proportional to the magnitude. And I know that since they are at rest, hanging there, their acceleration is 0, so the net force has to be 0. The only way the net force would be 0 if the forces add up to 0, so those have to be the same length. Okay, that's B. Let's do A. Okay, so here's A. Now again, I have the what long-range force? I have the gravitational force. I'm going to draw this force a little bit longer, but if I draw it too long, actually I'm going to move this down so I have room. I don't want to constrain myself and not have enough room. So this is MAG, and it's longer it should be. I didn't really draw it longer. There. Okay, that's the gravitational force on Superhero A. Now, what is touching Superhero A? This one is tough, right? If it's one single rope, it doesn't seem like there would be two forces acting on him, or her. But since the person's grabbing onto the rope, the top tension, the bottom tension actually can be different, and we need to represent those as different forces. Because imagine that there was a cut in the rope in the middle, so it went like this, and the superhero is holding the two pieces next to each other. The forces would be the same whether they're connected or not. Okay. So this T1 pulls down on the superhero. And so I'm going to write it as a downward pulling force. And notice that the length of this and the length of that, I drew it right, should be the same because it's the same force, right? This is the technically I think I kind of messed up. Because this should be, it's not technically the same force. Yeah, the problem with strings is that if we're using massless strings, I'm going to go ahead and draw a free body diagram for that string just to show you why we don't even care about it. So here's my string in between those two. I know that there is the person B pulling down on it because it's pulling up on that person. And that's going to be T B on 1. And then I know that person A pulls up on it, and that's going to be T A1. And those two forces have to be 0, equal because it adds up to 0. The string does not move. And there's no gravitational force on it because it's massless. So here I have these two ends of the tension, and I'm treating them just as one force. I'm calling them both T1. So T1 pulls up on mass B, it pulls down on mass A. Not the best, okay? But I don't want to make it too messy. But that would be your free body diagram for that string. So now I have two forces pulling down on this mass. Now, I want to point out that that's a tension pulling down. I do not have the weight of the superhero B pulling on A. It only is equal to that because these two are equal. It's not the same. It's not the weight pulling down on them. Okay. And then finally, I have the tension 2. I'll call this T2 pulling up. And now this plus this would be the tension T2. So it has to be equal in length to the sum of these two vectors. Now, some people write these vectors end to end like that. Either way is fine. I like it like this because it doesn't take up as much space, but you can do it either way. So that's the free body diagram for A. That's B. That's the middle rope. And then the top rope would look just like this one, except it'd be A2. It'd be T2, the top, whatever, and TA2, and the forces would be larger, but we don't need to draw those. Okay. Free body diagrams drawn. This one's not interesting because it has no mass. Now we can find, I want to find the magnitude of T1 and T2. That's what the last question was. So let's take this right here, and I can say F net vector equals mass B times acceleration of B. That's Newton's second law. And since they're at rest, AB is equal to 0, the 0 vector. It's useful to go ahead and pick my X and my Y axes. So I can actually write this as F net Y. The Y components of forces is going to be equal to the tension pulling up, T1, the gravitational force pulling down, minus MBG. Notice it's minus now because it has a minus Y component in that force. And that would be equal to 0. And then I can solve this for T1. T1 is MBG, which would be 55 kilograms times 9.8 newtons per kilogram. My calculator's way over here. Calculator time. Okay. On, drop, 55, 9.8, 539 newtons. Now what about the tension in the top? Well, let's go over here to this diagram and write the Newton's second law for it. I have, and I'll skip to F net Y is MAAY. That's the acceleration in the Y direction, which is 0 because, again, that superhero is at rest. So what forces act in the Y direction? Well, I have T2 pulling up. That's a scalar value because I'm in the Y direction. They're scalar values. T1 pulling down. MAG. Now, and the great thing about strings is that the tension is the same no matter which end you're looking at. The magnitude's the same. So I know T1 is this. I already solved for it. So if I solve this for T2, I get T2 equals T1 plus MAG. So that's going to be 539 plus 95 times 9.8. Calculator. Okay, 95, enter. 9.8 times 931 newtons. The end. And you know, I went through that in a lot more detail because I want to use it as a learning tool. And I do want to point out something that you don't want to do. And I see people doing this. They'll say, oh, I can draw the free body diagram for this. And they'll say, oh, the tension's pulling up, gravity's pulling down, and this person's pulling down too. And they'll write this as MBG instead of T2. And you will get the same number, but it's a bad idea. Okay, just because things work out right in the end doesn't mean that you should do that. Because that's not, the gravitational force is not pulling on mass. The gravitational force of B is not pulling on A. So if you put it there, yes, you get the right number, but it's the wrong way.